All right, everybody. Just trying to finish lunch, get this posted. We're gonna start the new unit on energy. All right, so energy is one of my favorite things to talk about in physics because it has such wide ranging applications, and it's such an important topic for our world, right? Energy. What is energy exactly? Well, that's a little bit hard to place your finger on or to put into words simply, but um, energy is the capacity of a system to do work. Well, what does that mean? Well, work is, turning a fan motor, turning an axle on a car, drive shaft on a car to turn tires. So um, it's a measure of how quickly something is moving along with its mass. Energy, it's an interesting thing. I think of it as the currency of physics, the currency of physics. And so, what does that mean? Well, a system. Take the systems we were just looking at with the ball rolling across a desk and flying off, or a bullet shot out of a gun. All right, a ball launched, something thrown off the top of a building, a basketball thrown off the top of the building. The system is the person, the ball, building, the earth. It's any of the things that are interacting via forces, right? That's your system. Um, the energy, for instance, if I throw a ball off of a building, the energy comes from me. I put the energy into the system by giving that ball what we call kinetic energy. Then gravity starts pulling it down, right? And the force of gravity starts to put more kinetic energy into that ball once it leaves my hand. So, um, energy is the currency of physics. It gets moved around in a system due to forces and interacting objects. So, the currency thing is going to have some applications going forward. I don't want to try to give it all away now. I want you to try to kind of figure it out from the simulation. So, um, when we had a really brief discussion in class about different types of energy, or words associated with energy that people thought of, and people said stuff like electricity, nuclear, thermal, fossil fuels, oil, gas, windmills, solar, all of those things. And those are great examples of energies in our daily lives, right? The power company, we call them, we actually buy energy from them. We use energy in our house, uh, and we buy energy. Gasoline stores chemical potential energy. When we burn it in our car, our lawnmowers, and all that stuff, we release that chemical potential energy as thermal energy, and we use that to cause something to move, basically, at the end of the day. Um, and well, windmills, right? We take kinetic energy out of the air, out of moving air, take its kinetic energy away, and put it into a rotating windmill. We use that rotating windmill to essentially pump electrons through wires. Same thing with a hydroelectric dam, right? We take kinetic energy out of water to rotate a turbine to push electrons through a wire. Nuclear power plant. We use radioactive decay to boil water to push steam through a turbine to turn magnets inside of wires to push electrons through wires. So uh, any electrical energy we use in our house is coming from a turbine or something rotating, which is pushing electrons through the wires. And then we tap into that energy in our house. And the power plant has to respond to that. It's what a brownout is when, for instance, you might have a brownout in the summer when it's really hot out and everybody's running their ACs, their air conditioners. Those are very dependent on use a lot of electricity. So the power grid, it has to keep up with that demand, right? So whatever's producing the electricity has to keep up with that. And if it can't, then you get a brownout where the energy can't have full energy everywhere out there. But anyhow, uh, in physics class, we start simple, right? We start with just some basic energy. So let me show you what they are here. fet.colorado.edu, go to simulations, physics. All right. The first one we're going to use is the energy skate park. So we're going to turn off all these. We're going to look at work energy power. Energy skate park basics. This one, whoa, this is a new one. New one. Ooh, I'm going to have to check that out in a second here. The basics one is a good way to start off, though. It's nice because this one just runs um, right in the web browser. Now, my picture is not blocking anything that interesting here. I'll move it over here. Uh, so what you can do here is grab the skater, let them go, and they go back and forth, which is what you'd expect, right? This is just the intro. So turn on pie chart, bar graph, grid just shows you heights, speedometer, and then you can change the mass as you go here. They have a few different shapes. So what's kind of interesting is you see it swapping between kinetic and potential, right? So these are bar diagrams. You can see it in the pie as well, right? The bottom, it's mostly green. So the bottom, we're at kinetic energy. The peaks are all blue, so that's potential energy. And then there's total energy, is remaining static. So energy is just switching between kinetic and potential, right? And just there's no friction in this. There's no friction in this. However, if I drop somebody from up here, I think I can get the thermal energy. Yeah, see that thermal energy? Thermal energy, sometimes also called internal energy, is the great destroyer of energy efficiency, right? If you compare, a hybrid electric Toyota Highlander versus a hybrid electric Toyota Prius, um, the Highlander gets far worse gas mileage, right? Even with the hybrid mode, and that's because it's got poor aerodynamics and it's heavier. Um, Aerodynamics, that turns into thermal energy, right? The more air drag in a car, the more resistive force there is on it, and you can think of that as thermal energy and or just a resistive force taking away energy. Um, Friction is the ultimate robber of energy efficiencies, and we have these things called ball bearings that help rotating shafts turn more smoothly, grease things, and so on. But anyhow, you're going to play with this app. You can try it on the playground mode. That's kind of fun because then you can make your own track. Uh, you can turn on friction, which is interesting. What you'll see here is you'll see the energy slowly get pumped up into thermal energy, right? In real life, obviously, this is what would happen. Slowly but surely, eventually, all the energy becomes thermal energy. Um, So you're gonna kind of figure out what kinetic and potential energy are based on the simulation. You're gonna play with it. There's another simulation too. So this introduces the first kind of three main energies of physics: kinetic, potential, and thermal. Thermal is often called also internal energy. Internal energy. We'll talk more about that in class. You go back to the website here. There is another energy lab, masses and springs. This one shows us the fourth physics energy that we like to see here. So we want to go to the energy one. My bad. It has a similar bar chart, but you'll notice potential energy is broken into two categories, right? So if I hang this mass off of here, I let it oscillate and turn down the dampening. So dampening is it's like friction in a spring, basically. It slowly loses its energy into thermal if you have dampening on. But let me, so I'm going to load the spring here and let it go. And it oscillates, right? It's kind of fast here to see what's going on. I think you can slow this down. Right, so you can slow it down to see what's happening. So it's gravity and kinetic and something called elastic. So the spring itself stores energy, right? You never get just a full bar of kinetic energy, right? There's always some gravity and elastic in there still. So that's kind of interesting. And I love this bar here, right? It's swapping between them all. The elastic energy is the greatest when the spring is stretched the furthest, which we'll see in class also. So that's the other energy. These are your main 5 energies we're going to have in physics: kinetic, gravitational potential, elastic or spring potential, thermal energy or internal energy, and then total is just the sum of all the 3. Now, conservation of energy tells us that that total energy will remain constant unless acted on by an outside force, so or some sort of dampening force. So if I change this, I grab this, right, and I change it, our total energy changes, right? I start acting on with outside force, that changes things. But once you let it go, as long as there's no outside forces, the total energy just remains constant. All right, we'll stop there. See you later.